I'm going to start talking about, we're going to talk about the vector space. Um, we're taking baby steps. Um, right now, I'm only going to be strictly talking about vectors the way I already defined them as meaning n-tuples. Good old vectors. Worry about other stuff later. So we say some set of vectors, space, which you may or may not be able to visualize or draw, is these two properties, or these two closure axioms that hold. If I take any two vectors in this set V, the result must also be in V. If I add any two vectors in V, the result stays in V. That's a test. If we multiply any vector in that set V by any scalar, and the result is also in that set, that space, then that's a test. And if it passes both tests, it is a vector space. When we're talking vectors the way we are, and we interpret them geometrically, these spaces are going to be seen as things like lines and planes and 3D spaces. So you can kind of visualize them just like vectors with the low dimension, etc. We can get away with just thinking about these two axioms because when we get into the general vector space, the good thing about the vectors, the way we already defined them, is they came along with, we define what we mean by addition, we define what we mean by scalar multiplication, we define what we mean by a zero, etc. So it came with all these operations and definitions to begin with. Later in the generalized vector space, we're going to have to add more axioms to cover things like that. But now we don't have to worry about it because we're only talking about vectors as n-tuples. Anyway, put these two combinations together, it means if I take any two vectors in my set, then any linear combination of them will also be in that vector space. So any vectors of that vector space, your linear combination of them will also be in the vector space. And if you think about this second test here, multiplying by a scalar, that scalar could be zero, right? So any vector space must contain the origin, because if you multiply it by zero and you don't get zero, didn't stay in that space. The whole, however many dimensions you got, say the 2D plane or the 3D whole volume or bigger, those are vector spaces. We might talk about why that's so in a little bit later. But here's some examples. Take a plane that contains the origin. If you add any two vectors in that plane, the result's going to be in that plane. If you multiply any vector by a scalar in that plane, the result is going to be in the plane. That is a vector space. You just had a line, you add any two vectors that are in that line, it's going to still be on that line. Or if you multiply any vector on that line by a scalar, it's going to be in that line. What am I going to say? Anyway, lines and planes containing the origin are vector spaces. Oh, this is what I'm going to say. You can't really sort of truncate it. I want to say these things have to go on forever. Well, let me talk about it on the next chart. For one thing, a subset of a vector space that is itself a vector space, meaning the subset is a vector space, and it obeys those two axioms, then we call it a subspace. It's a vector space, but is also a subset of another vector space. The intersection of two subspaces is a subspace. Like here, consider two of these planes. All planes contain the origin. The intersection of those planes will be a line. it's going to be a subspace. Even if it's tilted, you're still going to intersect at a line. Well, unless they're totally parallel to each other, they're the same plane. But even if they're tilted, they're going to intersect at a line, and that line will be a subspace. But if I took a vector from this guy and tried to add it to a vector from this guy, I'm going to get something in generally outside of either of those subspaces. So the union of two subspaces is not necessarily a subspace. Let's just think of, say, a line here in one of these planes. They intersect at the origin. Subspace. Make it your smallest subspace. Origin itself is a subspace. Any span is a subspace. Can you span a vectors? Because it's a linear combination of things, it contains the origin. It's a subspace. That's all I want to say for now. Next, get into talking about the dimension and basis vectors, vector space. Raining here.